Hello friends, here we are having one heat transfer problem in which there is a square plate of silicon material. Over this square plate there are a number of fins attached and water is flowing over these fin surfaces so that the heat transfer from the fin surfaces and the heat transfer from the unfin surfaces due to convective heat transfer taking place at the top surface and at the bottom surface. There is a heater which is maintained at a temperature of TH is equal to 90 degrees centigrade. So in this problem we have to find out how much the rate of heat transfer from this bottom heater to this flowing water. The water is maintained at T infinity is equal to 20 degrees centigrade. So to find out this heat transfer rate, we have to draw the thermal resistance network and we have to calculate the thermal resistance offered by these fin surfaces and the thermal resistance offered by this unfin surfaces and the thermal resistance offered by this conduction plate or the base plate. By knowing all this thermal resistance we can draw the thermal resistance network, and by knowing the thermal resistance network and the temperature difference between these 2 points we can find out the heat transfer rate. So to do this, first of all we have to find out the number of fins attached over this square plate. In the question it is given that the plates is having the fins separated by the same dimension of the space between each fin. So we can say that the fins are equally spaced or alternately attached to the square plate. The square plate is 3 cm into 3 cm. So we can determine the number of fins by this method, that along this length how many are the square can be placed. So we can find out the number of fins by this method, that the number of fins in a single row, this is the length, this is length 3 into 10 raised to power minus 2 meter. This is also 3 into 10 raised to power minus 2 meter. So 3 into 10 raised to power minus 2 meter divided by the number of square, and the number of fin is the half the square. So we can determine the number of fins like this method. This is the number of fins in a single row, and this is the number of row along this height. So we can find out the number of fins as n is equal to 5 into 10 raised to power 5. So by knowing the number of fins we can determine the total resistance offered by this fin, and by knowing the unfinned area we can determine the convective heat transfer resistance. Convective heat transfer resistance as 1 over h into unfinned area. So we have to find out the resistance offered by finned area and the resistance offered by unfinned area. So the resistance offered by unfinned area can be calculated as 1 over h into area of unfinned surfaces. Unfinned area surfaces can be calculated as area of the square plate, 3 into 10 raised to power minus 2 square minus n is the number of fins into dimension of each fin, area of each fin. So by doing this we can calculate the total unfinned area, and by putting in this expression we can calculate the convective resistance offered by unfinned area. So this is the convective resistance offered by unfinned area. Now the resistance offered by finned area can be calculated by this method. We know Q fin equals to under root HPK and hyperbolic MLC and delta T. This equals to delta T. This equals to delta T. Why we are taking MLC and LC corrected length? Because this fin is of finite length, that is equal to L, and uninsulated tip. So we are using this formula here. LC can be written as length plus half of the thickness, that is given as 30 micrometers. So corrected length is this. Perimeter P can be calculated like this, because the field is the square of 30 micrometer. This is 30 micrometer, this is 30 micrometer. So we can calculate perimeter like this. M can be calculated by putting all this parameter. So we can calculate resistance offered by single fin, because Q is equal to under root HPKA tan hyperbolic MLC into delta T. So R is equals to under root HPKA tan hyperbolic MLC raised to power minus 1, because Q is putting as Q is equal to delta T upon R. So this R can be assumed can be equals to this quantity. So by putting all these values, we can calculate the resistance offered by single fin. By knowing the resistance offered by single fin, we can calculate the total resistance by assuming that all the fins are parallelly connect between base temperature TB and the atmospheric ambient temperature. So these are the number of fins, and so we know if all these fins are parallelly attached, the equivalent resistance offered by this fin equals to 1 over n into resistance of a single fin. So by doing this, we can calculate the equivalent resistance offered by the fin. Now third one is the conduction resistance offered by the base plate. This is the base, this is the plate, square plate, this is the square plate, over which the fin are attached, over which fin are attached, over which fin are attached. This is the fin, this is the square plate, and this is the heater. T is equal to 90 degrees centigrade. Heat is going like this. So this base plate, this also offered a conductive resistance. Conductive. We know from Fourier law that Q is equal to minus K dt over dx. So R equals to dx over K. This can be written as dt over dx over K. We know the dimension, this is equals to D. So D upon K can be treated as the thermal resistance offered by this base plate. This can be found out by this method. Now by knowing all this resistance, we can put into the resistance network. This is the network here. This is the resistance offered by unfilled area. This is the offered by filled area, and this is the conductive resistance. So by knowing all the resistance, we can find out the equivalent resistance. After knowing the equivalent resistance, we can find out the heat transfer rate by using the formula that Q is dot is equal to delta T upon R equivalent. So we can find out that the heat transfer rate equals to 4.399